Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm glad to have Rani as our speaker today. Rani is a researcher in the machine learning department of Microsoft Research. And before joining the department, he was applied researcher in Bing. And he obtained his PhD from Hebrew University in computer science.
Thank you, Danny. So I'm going to be talking today about the median hypothesis. This is a joint work with Burges. And to begin with, I'm kind of to lay the ground, I'm going to discuss the PAC-Bayesian point of view about learning. And then we'll use that in order to define the median, and actually we'll find out that we need also to define a depth function by which we'll define the median. And once we have it, we'll be able to provide generalization bounds using for the median hypothesis, or actually what we will call deep hypothesis. So this would be the first part of the talk, and in the second part we'll start discussing algorithms. So the first one would be, how do we measure the depth of an hypothesis, and then we'll discuss how do we find the deepest hypothesis, which is actually the median. So this is what we kind of the outline of the talk. So let's start by looking at the Bayesian point of view on learning. So many learning algorithms look kind of like that. We have some sort of a scoring function. I will call it the energy function. And we give a score for every hypothesis based on some regularization term, pick your favorite, L2, L1, whatever, and a loss function on some observation that we had. From PAC-Bayesian point of view, we can look at it in the following way. We can say that actually the regularization term is actually represent some prior belief that we had. So think about the regularization term as the log likelihood of the prior belief that we had. And then given the observation, we generate a posterior belief. And this is what we use then to select an hypothesis and make a prediction. Now it's very important to note that these are beliefs. So it doesn't mean that we assume that something in the real world really behave according to these probability measure distribution or whatever you call them. This is just a representation of our internal beliefs on what's going on out there. So from kind of the way I would like you to view it is that the process of learning is made of three stages. We begin with some prior about the world, and then we see some evidence. So for example, it could be labeled and unlabeled examples from which we generate a posterior. And then once we have this posterior belief, we select an hypothesis with which we'll go ahead and make our forecasts and predictions. And actually, my talk today is going to focus on this part. Once we have our posterior belief, what hypothesis should we choose to use to make our predictions? So let's look at some common methods of selecting the hypothesis once we have our posterior. So one option is to use the maximal posterior, or this is actually what SVM and Lasso does. Actually, minimizing the energy function is equivalent in my language to selecting the maximal posterior. Another option is to use the Bayes function, right? Which means that every time I want to make a prediction, I will just hold the vote among all hypotheses. I'll do a weighted voting and make my prediction. I can use Gibbs sampling, which means just sample at random one hypothesis from according to your belief. And I can use ensembles, which are kind of an extension of the Gibbs sampling, which is instead of just selecting one random hypothesis, I will select several and just hold the voting between them. So I would like to compare these methods, but this is very qualitative comparison, and to make sure that you don't think that there is anything accurate about it, I drew it by hand. So just to emphasize that. And I want to look at two axes. One is the runtime. So when I want to make a prediction, how complicated is it to make this prediction? And the second axis is accuracy, but think about accuracy more as how well does it capture my beliefs? So I had the posterior belief, does the hypothesis, how well does it capture, all the structure of my belief? So let's look at some examples. So if we look at the Gibbs method, which is just, I got my belief, I selected a random hypothesis, and then I'm just going to use it to make prediction. So the runtime is really easy. I just need to evaluate a single hypothesis and see how well it works. But does it capture all the complexity, all my belief? To a very small extent, I would say. If we look at the maximal a posteriori, it seems to capture more, but still, it just looks at the peak, right? My belief can change dramatically, and still the peak, as long as it remains in the same place, I would pick the same one. So it doesn't seem to capture all that I've learned in the learning process. On the other hand, if we look at the Bayes classifier, it uses a lot of information about my belief, but it's in terms of runtime, I need to really hold a vote every time I want to make a prediction. Ensemble method provide kind of a trade-off, right? If I use an ensemble of just one hypothesis, then this is just a Gibbs sampling, so it's going to be fast, but not very accurate. Whereas as I get my ensemble to grow larger, then I capture more structure for my beliefs, but it becomes slower.
You're making some assumptions.
Of course, this is...
Because, for example, for linear, if your distribution is over linear classifiers, then you can show that the Bayes optimal, I think, is also itself a linear classifier, right? So somehow, the fact that the Bayes...
No, the Bayes is not linear, is not... if you're making a binary classification, so it's true if you it's not true that the Bayes, if you take the Bayes classifier over linear classifier, is a linear classifier. It's simply not true.
Well, maybe it depends what your distributions are. When they do when you have PAC-Bayesian generalization bounds for SVM, then in that setting, it turns out that the Bayes classifier is in fact very fast to evaluate.
Again, this is very, this is why I didn't, I drew it by hand. It's a think about the concept, not about the very specific cases in which things might be different. But generally speaking, computing the Bayes classifier is hard. Although there are examples in which it is easy. Generally speaking, for general class with general distribution, this tends to be hard. Okay?
So one question. If I think about this in a Bayesian perspective, there's two types of uncertainty. There's model uncertainty, and then there's parameter uncertainty. And so it sounds like you're talking about just model uncertainty in this kind of schematic diagram. Is that right?
I'm just talking, so again, I'm isolating all the problem of estimating the parameters and everything. And I assume this is after I had my prior belief and I saw some evidence. And this is currently my belief. This is my belief and, this is it. But now I'm asking myself, okay, given that this is my belief, how should I make predictions?
So you're thinking about distributions over model classes and the parameters for those models.
Yeah,
so you're thinking about both model and parameter uncertainty.
Exactly.
Okay, great. Thanks.
So what I'm about to propose is a new way to select an hypothesis from my belief, which is to use the median. Now, the median is going to be just a single hypothesis. So in terms of runtime, it's going to be equivalent to the Gibbs and the maximal posterior. But I will select this hypothesis that captures as much as possible information about my belief. So this is where we're heading to. Okay, is it? So Now I want to start defining what do I mean by a median. But it turns out that in order to define a median, we'll need to define something which we'll call a depth function. So let's start with just the case that we all know about the one-dimensional univariate median. So assume I have this sample here of points, and I want to find the median of these points. So one way to look at it is to say the following. Every point kind of splits the sample into two parts. All the points that are to the left and all the points that are to the right of this point, right? And we associate a depth with each point being the size of the smaller part. So for example, for this point, it had the depth 3 because here on this side, there are only 3 points, right? Where this point has depth 1 because, yeah, if I split the space, only this point is on this side. Now, given this definition, then this point is the deepest point and it is the median, right? Once we define the median via a depth function, we can now move to multivariate cases.
So you don't consider the real distance in the
Sorry?
So you don't consider distance in the
No, I don't consider distance. No, just count the number. Just count the number, right? So let's try to see if we can extend this definition to the case, the multivariate case. So when we move to the multivariate case, this is called the Tukey depth function and the Tukey median. So how do we define it in the multivariate case? So assume again, I have this sample, but now it's two-dimensional. And I want to measure the depth of every point. So what I do, I look at hyperplanes. So if I want to compute the depth of this point, I look at all the hyperplanes that go through this point. Every hyperplane split the sample into two, and I take the smaller part of it. And I take the minimum over all hyperplanes. And this would be the depth of this point. So for example, you can see for this point, the depth would be 2, because every hyperplane will have this point and at least one additional point with it. Whereas for this point, the depth would be 3 because every hyperplane will have at least this point and 2 other points with it. So this point is deeper than that point. And again, once we have a depth function, automatically we get a median associated with it, which is just the deepest point. Now, a word of advice is you have to know that in the multivariate case, actually there are many definitions of multivariate medians. So we can define different definition of a depth function. Each one of them will lead to different median. Yeah.
But if in that example, if your points are on a convex shape, right, then all of them are medians.
No.
Oh, because you're saying no, because all of them will have one that is one.
So remember that the median doesn't have to be a sample point. So if I have points on a circle, right? So let me draw that. Right, I have points on a circle, right? This is my sample. So you're right to say, you're correct that every one of these points has a depth of 1. But actually that point is much deeper.
Also, it's any
I can compute it for any point in space, right? And in this case, you can actually see that the median is actually the center. So it's what you expect it to be.
What if you can, in this case it's easy to compute, but what if you cannot compute your function in that point, or that's never the case?
So there are depth functions that are defined only on your sample, and there are depth functions that are defined everywhere. There are different definitions. Each one of them has its pros and cons, right? It's an interesting topic. It's a very interesting topic, but I'll have to skip on all of that. So I just wanted to point you out to the fact that this is not the only way to define a multivariate median. But this is the one that I'll be inspired by. So this is why I brought it up and not other possible definitions.
So how do you break the tie? I assume you several points will have the same depth.
Okay, so for example, again, like the median, like the univariate case, there could be more than one median, right? You know it from the univariate case that the median is not a single point, it could be. But here you can show, for example, that the level sets of the depth functions are convex. And therefore, if you have more than one median, it always will be a convex set of points which are the median. So you can show all sorts of things. So there's a lot of study on multivariate median. You know, just as an anecdote, I will tell you that about 10 years ago, it's the first time I encountered that, and I thought that I invented the multivariate median because I searched for multidimensional median, and when you search for multidimensional median, I couldn't find anything. And I thought, you know, this is my big thing, right? And then, I don't know, I know why. A friend told me, oh, you know that in statistics, they don't call it multidimensional, they call it multivariate. Yeah. So this is why I brought this, just to mention the fact that there is a lot of literature, a lot of different definitions, and unlike the univariate case in which when you say the median, we all know what you're talking about, when you go to the multivariate case, this is no longer true. But now I'm going to, motivated by this very specific definition of median that we just saw, I'm going to define a median for function classes. So one thing that is important to note that unlike what we discussed before, in which we thought of a sample of points and we wanted to find the median of these points, now we're talking about functions, right? We're not gonna find the median of our sample, but the median of our hypothesis. So, just a little bit of notation that we're gonna use. So our sample space is gonna be, I'm gonna use the letter X for that, and the function class is F. And the most important notation is Q, which is our belief, our posterior belief. This is the distribution over our sample class. And here is how we define the depth in this case. So first, I'm going to look, I have a function that I want to measure its depth. So first of all, I take an instance and define the depth of this function with respect to this instance x to be actually the probability of a random function agreeing with the label of f that f assigns to x. Okay? And now I define the depth of f to be just the infimum over all instances. So think of it, it's similar to what we did in the Tukey depth, in which we said, okay, every hyperplane defines some sort of a depth because it splits the space into two, and I take the smaller part, and then I take the infimum over all hyperplanes. This is what we do over here.
This is in the function family Q, like any, does it have to be a parametric space or? Just symmetrical.
Actually, I can compute the depth of a function which is not in my function class, for example. It's defined for every function, right? And again, once we have a definition of a depth function, we have a median, right? Which is just the deepest point.
Ronnie, I have
Yeah.
a question. So in the previous slide, you said that the range of f is just minus 1 plus 1, right?
Yeah.
So there's just two depths.
No. For every, again,
Given an x,
for every x, it could be for.
of x is either 1 or minus 1.
Yeah, but then I take the infimum over all x's.
I understand, but for given x,
Yeah.
there are just two types of
Yeah.
f's, one that are deep and one that are
Exactly.
shallow.
Exactly.
Okay.
Yeah.
Wait, but there's a probability of when you draw f prime at random q.
Yeah, but what Offer says, if I have for a certain point, and we'll see it in a second, for a second point, say 80% of the functions say that the label is +1, and 20% will say that
So
is. So it's either you're in this class or in that class.
There's two sums, there's two terms in this one.
Yeah. But once you take the infimum, then this function becomes continuous, obviously, right? Yeah. You're absolutely right. Now.
Wait, hold on.
Sure.
So you're taking infimum over all of x, regardless of mu.
Yeah.
So if there's an x with no probability of ever occurring, you still care
Good
about.
question. wait 5 minutes.
So the depth of F is the amount of support that it gets for its least popular distribution.
Exactly. So for example, you can see that if I'll compute the depth of the Bayes classifier, it will always be at least half. Right? Do you see that? Because the Bayes classifier always takes the majority vote. Right? So for every x, at least 50% of the population will agree with that, and therefore the infimum has to be greater than half. Right? So this is and keep that. This is an example to keep in mind. So a depth of half is kind of the best we can hope for in any realistic setting. Right? And the question would be, how close to half can we get? Just, I will not go over all the details here, but we can actually see that the Tukey depth that we discussed before is actually a special case of this definition. So when the hypothesis class, we treat it as some sort of linear classifiers, then actually the Tukey depth becomes, a special case of this definition. But there are some interesting things about the Tukey depth. So for example, we know that the Tukey depth, if we work on a d-dimensional space, there is always a point with depth greater than 1 over d plus 1. Regardless of the distribution, there is always a point with depth 1 over d plus 1. And we know further that if the distribution Q is log concave, then there is always a point with depth 1 over e, regardless of the dimension. Right? Now, 1 over e is very good. Remember that kind of the optimum we hope for is 1/2. So 1 over e is very close to that.
Right. So the Bayes point isn't always the Bayes function isn't always in this space F. That's what you're saying.
No, it doesn't have to be in space. It could be
unrealizable. So you might not be able to realize in the space with the measure Q that you can get a half. I see.
Exactly.
Okay.
Exactly. Now, if we go back to the beginning of our discussion, and we said, many learning algorithms look like that. The energy function looks like that, and we actually like the loss function to be convex and the regularization term to be convex, which means that the energy function is convex, which means that Q is log concave. So actually, in many of the cases which we really work with, we are exactly in the setting where our posterior belief is log concave, and therefore we are guaranteed to have a deep function, a function with a depth of at least 1 over e. So I hope that you get some intuition with respect to the median and the depth and what does it mean. And now I would like to convince you that the median hypothesis is actually good, right? But before I do that, again, a warning: don't always use the median. But in our case, it's actually good to use the median. And so here's the first result. So let's say we have some target. So the word is distributed with some distribution nu that I don't know about it. And say we'll use our R nu of f is just a generalization error of f. So we can prove that for every function f, its generalization error is bounded by 1 over its depth time the expected generalization error of if I would have just sampled hypothesis from Q. Okay? And actually the proof is trivial. Right? The proof, we have to consider just 2 cases. Pick a point. There could be 2 things. If the majority vote is done with large majority, then my function, since it is deep, must agree with the majority. Right? And therefore, my risk, my loss on this would be very similar to the risk of just a random hypothesis. The other case is in which, Q is not decisive. In which case, if Q is not decisive, my competition, right, which is just a random hypothesis, would err a lot, regardless of what is true, and therefore I can't do much worse than that. So again, this is kind of vaguely speaking, but when you write it down, it's just 2 lines, and you get the proof. The nice thing about it is that we can connect that with the kind of more traditional PAC-Bayesian analysis. So we had just about a month ago, we have Mario Marchand over here, and actually what he showed is something of this type of a theorem, and trying to clear things around. Basically, what it says that with large probability, the generalization error of just selecting an hypothesis at random, the expected error of a random hypothesis, is bounded by a term which is made of 2 things. One is its training error, and the other one is kind of the KL divergence between the prior and the posterior. And now we can just take this result, take the theorem that I just showed you, and plug them together, and we get a generalization bound that say that for every hypothesis, its generalization bound is bounded by 1 over its depth time the same term that we had before. But now there is something really annoying about a definition, and Ofer asked about it, is that we looked at the infimum. When we defined the depth, we looked at the infimum, and this seems to be kind of very harsh, right? It could be that we have a function that agrees with the majority on almost all the points, but say 1 point. So it seems not the right way to look at it. And therefore, we can define a relaxed version of the depth, in which we say, instead of taking the infimum, we say, okay, you're allowed to put aside a proportion delta of the points and compute the depth only on the rest of them. So when we look at this relaxed depth over here, actually what it means that for the majority of the points, your depth is greater than that, but there might be a proportion delta in which actually you do worse than that, but that's fine. And again, we can repeat the same kind of proof that we've seen before, the same kind of theorems, using this relaxed version of the depth function. So we can bound the generalization error in terms of this relaxed depth function, and have a delta term over here. And again, we can plug it in the PAC-Bayesian bounds and get a generalization bound in terms of this relaxed depth function.
I mean, this holds uniformly for all delta prime? Or I can choose delta prime to be whatever I want?
I think you can, but I think you can, but I need to verify that. I think it does, but. So, I hope that by now I motivated you that finding a deep hypothesis is something worthwhile. And now we start looking for, to find a deep hypothesis. And then the first thing is actually to be able to measure the depth of an hypothesis. So if someone comes with an hypothesis, can I know what its depth? So, and we want more than just estimating its depth. We want a uniform estimation, meaning that if I have a class of function, I want to be able to estimate the depths of all of them simultaneously and make sure that my estimate holds for all of them. So here is what we're going to do. So assume I have a bunch of points. And as we discussed earlier, for each point, I can look what is the size of the population that labels it +1 and what is the size of population that labels it -1. So say these are my sample points. And now I want to evaluate a special function. So this function for the first point, it provides the label +1. Right? So I know that its depth on this point is 20%, because only 20% of my functions agree that the label here is +1. And then I can take the label on the second point and again see what is the size of the population that agrees with it on the second point. And so on and so forth. And I can go over all the points and each one of them mark what is the depth with respect to this very specific point. And eventually the depth is just the minimum over that. Right? So in this case, on this point, I had the smallest agreement, and therefore the depth of this function is 0.2. Right? And this is what actually we're going to do. So actually what we're going to do is instead of computing the infimum over all points, we're just going to take a sample and evaluate the depth only on this sample. And when we want to evaluate, what is the agreement here, again, we'll take a sample of functions and use them to evaluate, what is the proportion of the population that labels +1 and what is the proportion of the population that labels -1. And this is actually what the algorithm does. So you take two samples. One is unlabeled samples of instances, and one is a sample of functions from your belief. And you actually compute for every point x. You compute what is the proportion of the population that agree with the function that you're trying to evaluate, and you take the minimum, and this is your estimate. So this is what we call the empirical depth of the function f. And we can prove the following property, and again, I'll try to clear up all the details here, but the main thing is that with high probability, we'll have the following. The depth, the empirical depth we compute is going to be greater than the true depth minus epsilon. And it's going to be not larger than the relaxed depth plus epsilon. So it's going to be somewhere in this range. But this holds, with high probability, it holds simultaneously for all functions. So it's uniform. This is a uniform bound that holds for all functions. And if we look at the probability term, what do we mean by high probability? Let's look first over here. So we have here the phi function, the gross function of VC dimension that we're used to see. And we see that we have some polynomial term here, but exponentially small term over here, and the same thing over here. So we can choose the sizes of the sample that we need, such that the probability will be as high as we want, as close to 1 as we want.
So is epsilon tied back to the fraction in the relaxed depth? Because you have a sort of hidden parameter, right? In other words, if you go back to the definition of relaxed depth, there's a parameter you choose, a delta.
Delta. Here it is.
Oh, okay. So that delta is.
This delta is.
Where is
here,
it? Oh, there it is. I see.
Here.
Okay.
And again, I'm going to skip that. The proof is, again, very simple. Is the main ingredient is to note the following, that if I have in my sample, so we have this slackness between the true depth of a function f and its kind of relaxed depth. Right? We have a sort of a slackness here. If my sample of points consists of a point for which df of given x is somewhere in this range, then my estimate would be smaller than the relaxed depth. And my estimate will always be greater than this depth, because this is the infimum. So all that I need to guarantee is that my sample is actually a heating set, which means that it heats all these regions. So I have instances in all these regions for all the functions. So this is called a heating set, and in the kind of in the machine learning literature, this is called an epsilon net. So we know that if the VC dimension is finite, a random sample will actually heat all these regions with high probability. So this is actually, the main ingredient in this proof. So now we know how to measure depth, and we know how to measure it uniformly for all the functions in a class. But now we would like to find the median, or approximate the median. We want to find a deep point. And this is what we're going to do now. And again, I want to start with kind of a motivation. So I'm going to show it by pictures and then go over the algorithm. So again, I have this sample of points, and actually, I'll tell you in advance what we're going to do. Instead of trying to find really the deepest point, the deepest function, we're going to find the function that maximizes the empirical depth and not the true depth. And it turns out that it is easy to find this function. So assume I have this sample of points, and on each one of them I know what is the size of the population that labels it +1, and what is the size of the population that labels it -1. So I would like the deepest possible points will actually agree with the majority vote on all these cases, right? So the Bayes classifier will give the label -1 here and +1 over here and +1 over here. Because the majority says +1, then so if I can find a function like that, this is the best that I can hope for. But now assume that I cannot. So I can't find any function in my class that actually gives all the correct labels on all these cases. So I'm going to eliminate one of the points from the sample, saying that I allow the function that I'm looking for to kind of mislabel this point. But which point do I want to eliminate? If, for example, I'll eliminate this point, I might get a classifier that labels here +1, and its depth is going to be 0.2. So this is not very favorable.
Quick question.
Sure.
How are you drawing these graphs? Are you sampling from the posterior first?
Yeah. So I want to eliminate the point on which there is the smallest margin in the voting. Because I know that for this point, so for example, for this point, although 55% of the classifiers labels it -1, but still 45 says +1. So if I got the label +1, this is not too bad. So I can delete this point and say, can I find a classifier which agree with all the remaining labels? And I can keep going, and every time I will delete the point on which there is the smallest margin. And I'll keep going until I'll find a consistent classifier. And not only that once I found one, I know that it is actually maximizing the empirical depth. I can also know what is the empirical depth, and the empirical depth is actually the size of the minority set on the last point I deleted. So, and this is basically it. So again, the algorithm itself will receive two samples. One is unlabeled sample of points. The other one is sample of functions for my belief distribution. And the output would be a function f which actually maximizes the empirical depth and its empirical depth.
Why do you need unlabeled sample of points? Can't you do the same thing with the sample, the labeled sample?
The labeled sample is something that the only thing that I get is a posterior. You might have used I don't know what you can use. I don't know what have you used to reach with this posterior. Maybe you didn't use labeled sample. Maybe you have some oracle that gives you some hints about I don't know what. But once you have this posterior, this is what I need in order to select the median hypothesis. Does it make any sense?
Yeah, but I'm saying why can't you can use a sample?
I can use this. I can use label sample, but it doesn't add anything. I don't use the labels.
Yeah, I mean what I'm trying to say is having unlabeled samples doesn't add to anything at all. I mean, when you're training an algorithm, you have a set of labeled points, right? So using additional unlabeled points is not adding to anything either.
You're asking whether if I trained using a labeled example, can I reuse the sample again for this part?
Yeah, and I think you should be.
You should be. You should be. You can kind of the delta term in the confidence, you should divide it by 2, and you should be fine.
You have T. You can build an ensemble over T.
Mm-hmm.
Is it true that this ensemble will always be better than your median?
I don't know. It needs to be evaluated. But again, this ensemble, in terms of when I want to really use it, it is much heavier than having just a single hypothesis, right?
It's n times heavier.
But on runtime. And here I use it only in training.
Right. I understand.
Yeah.
But is it true that that the best you can do, the best you could hope to do, is as good as the ensemble on this guy? Because you're optimizing this.
It makes sense, but can I prove it? I don't know if I can.
The ensemble, you just take all weight 0 but the median.
Sorry?
You can have in the ensemble all weight 0 but 1.
But here's the proof. The proof is very easy, Ron. If you have Q prime, which is not the posterior, but it's the empirical posterior, just the posterior is defined by this, then the ensemble on T is the base optimal on that empirical posterior.
It's true, but it's not my. But then you have to prove that this empirical posterior is better than the.
I mean, that's the optimal classifier on an average, right? You can't do better than base optimal on average.
On that
on that Q prime, but we're asking on Q, right?
Right.
Okay, so I think the answer is that the best upper bound for this ensemble is better than the best upper bound you can get, but we don't have lower bounds.
Yeah.
So this, go ahead.
Well, I was just going to say, I mean, the case of the base point machine is a classic one, right, where it's known, and you're referring to this earlier, where, in fact, you know, the actual the BPM, so to speak, is an approximation because the actual classifier that you may want to get out of it may not live within the function class you're trying to get from. So it could be that the best ensemble out of T, you know, does pretty well. But if you happen to have a Q prime which you're using and optimizing against that had that magic function, you could do better than what was actually from the ensemble. So
if you can use an ensemble, yeah. And if you can use the base classifier, probably the best thing that you can use. But if you can't,
you know what this reminds me of is Rich Carana's whatchamacallit trick, the thing where he made this gigantic loaded mega classifier, the mega ensemble, that sort of triggered. Is Rich here? There he was. What do you call it? The trick, your trick where you make the ginormous sort of classifier out of everything and the kitchen sink.
The ensemble selection.
The ensemble selection. So that's sort of your F. And if that's sort of, it's going back to Chris Meek's question of like, what is this? Is this like a parameter space? No, it's this really hairy, weird space over, you're saying that your belief is, I don't know, I'm going to try decision trees and all sorts of things. And that's sort of what your sort of giant belief domain is. And instead of what you're doing is you were sort of, I forget if you were boosting or averaging them together. He's saying you could train a little classifier using his method, maybe. And this is sort of a guidance of how you would train the little classifier on the ensemble.
The caveat is you have to find one guy who agrees with a lot of other guys.
But this is usually easier. So, you know, if you think of the task, usually when we say we want to find a classifier that minimizes the number of errors, stuff like that, this is hard, right? But so what I need is an algorithm, this is what we call here the consistent learning algorithm, is an algorithm that either say, I found an hypothesis would agree with everything, or I failed, right? If
train something, you see if you get 0
The
training.
question is when you're building ensembles, you're usually building ensembles over very, relatively simple base hypotheses, right?
Well, he did like everything, every imaginable algorithm was in his
So
ensemble.
your ensemble is much more expressive than any one of the individual things.
Correct.
And here, Ronnie's saying, I want to find one guy who tends to agree. Let's say you use all these things to.
To simplify the notation, I assume that the functions here are from the same class from which I'm trying to select the final hypothesis. But actually, you don't have to make this assumption. It just otherwise I have to hold 2 function classes and all the discussion becomes cumbersome. But actually, it could be that the ensemble is made of some stumps and then you try to learn a tree.
You're doing this picking.
Yeah. See what I mean?
So we also did, but still, John, you're not.
What?
You're missing something. So if you take 1 million things and you build an ensemble over them, and you're trying to find one thing which tends to agree with that ensemble.
Yes.
I agree that Rani's saying it could be like a big, huge tree, but it's going to be a big, huge tree. So you're going to pay again with computational complexity, because if you want a very expressive function like this, you're going to have to make it complicated.
No, that was the beautiful thing that Rich found, because he had, if you want to talk about it, I mean, he trained all this insanely complicated ensemble. I mean, they were just enormous, I don't know, 100 times slower than you would ever want to use. But then he would label, in fact, a very large training set. It's sort of different from here. You would label a very large unlabeled data set, and then you could get a much larger data set. Here he's saying, well, maybe what you do is you just find the largest training set that you can get zero training error on, that matches the labels of the giant mega ensemble. So it's sort of a different way of training Rich's giant mega ensemble.
Well, you guys are saying yes, but I think you're missing but let's take it offline. I mean, there's a problem with what you're saying. You can't eliminate the bias variance trade-off. I mean, you can't get something for nothing.
I tend to agree with you. If you don't have any limitations in runtime, then use your more sophisticated ensemble. Use a Bayes optimal, right? I agree with you. But if you have limitations in runtime, and you want to moderate the size of your hypothesis because you have this limitation, so this is how I propose to do that.
That's exactly the motivation for this ensemble system.
Exactly. So you can build during the training process, right? You can build this huge ensemble, right? And this is actually here. This is the ensemble. But now, still on the training process, you have to prune it. So you can look at it. I think this is what John is suggesting. You can view all this as a pruning process.
I saw Rich's motivation a little bit differently, because I thought like my perspective on maybe this is radical, but my perspective on Rich's work was that, like, I mean, I agree with you philosophically. It feels very similar, but he was kind of like, okay, here's a small set, and on this small set, I can't train a really simple thing to generalize well, but I might have a really complex algorithm that can do a good job. So I had a whole ton of them, and then I classify a bunch of unlabeled data with that, so I effectively expand the size of my labeled data, and then I train a simpler classifier on it. But here, it doesn't seem to be so much, at least the philosophical perspective doesn't be so much that, like, oh, I have too little data to work from. It's more that, well, I mean, maybe, I don't know, it's not so different, but it feels like you're trying to just say something about generalization being, well, maybe it comes down to the same thing. Yeah.
Basically, I separate the task of the data, the training data. It's just out of the picture over here, right? It's just out of the picture. And the same thing is in what Rich did, because once you train these little models and you now use them to label new data, you didn't add new information, right? You didn't add new information in this process. Sure. This is just a method by which you actually select your final hypothesis. So here I just instead of just gluing them together, I said, okay, do whatever you want to do in the first part.
So somehow you get
here is what you do on the second part, and I'm just analyzing the second part. Do whatever you want to do on the first part.
So I'm just trying to understand your algorithm a little better. How does it prevent situations like that on the board that you just drew, and that your set of sample functions, none of which are particularly deep?
So again, when the function that I'm going to find eventually does not have to be one of these n functions. It's not going to be one of f1 to fn. It could be any function in my class. So I have this algorithm A, for which I'm going to feed it with samples, and it just either tells me no, I can't find. I'm going to feed it with labeled samples. Points.
Labeled by the
ensemble. They're going to be labeled by this ensemble, right? And then I'm going to feed it samples, labeled samples. And this algorithm will either tell you, no, I can't find any hypothesis which is consistent with this sample, or will say, hey, here is an hypothesis which is consistent with this sample. And this hypothesis doesn't have to be from this f1 to fn. It could be anywhere. And actually, and this is, I didn't want to talk about it, but we already discussed that it doesn't have to be in the same class, actually. And the algorithm, okay, just, the algorithm, what I do in first I compute for every point kind of what is a proportion of the classifier in my ensemble, actually, that label it +1. And this is a PI plus. And then I compute the size of the minority group on each point and sort the points such that the first point will have the largest minority group and the sizes of the minority groups are actually decreasing. I compute the label of the majority vote, kind of what is the label that I really want to have, and start iterating. So the first thing, I'll just put all the points in with the labels of the majority vote and see if I can find a classifier that just classifies correctly all of them. And then, so I'll call the algorithm and see if it can find a consistent hypothesis. If it does not, I'll remove the first point. The first point is the one with the largest minority. So I'll remove it. And again, send it to the algorithm. And I keep going, until eventually the algorithm will return a function.
Why not do a binary search? Why do a linear scan? It seems like you're asking for...
You can do that.
Okay. Just that's log n versus n.
True.
Number of trainings that you have to do.
Actually, yeah, that's right. But it doesn't matter for us.
Oh, you're saying knock off half the
Well, yeah, because otherwise you have to train your neural network or whatever.
Sure. You're right.
Is it guaranteed that it's true or is it not?
Is it?
Well, I mean, couldn't it be the case that that's not monotonic?
No, actually, it could not. And eventually, once the algorithm returns a function which is consistent, then I can just compute its depth using, the formula here. And we can prove the properties of this algorithm. So first of all, it will always terminate. So it couldn't be that you'll keep the leading points and end up with an empty sample, right? And the reason is very trivial. On the last point, you give it a single point with the majority, the label that the majority gave this point. Right? So there must be a hidden hypothesis which agree with that. And we can show that the function that this algorithm returns is actually the maximizer of this empirical depth. And the depth that it computes is actually the correct depth for this function. And again, trying to clear the clouds around this formula, the important thing is the following. The relaxed depth of the returned function is at least as big as the depth of the median. So this is a supremum of all the depths. So this is actually the depth of the median point minus 2 epsilon. Right? So actually it does approximate the median. So before I conclude, just a few small notes. So one is, we discussed in the beginning, actually, the motivation for the definition of the depth were the Tukey depth and the Tukey median. So now we can go back to that and say that actually the algorithm that we described, actually, if we use them on this very specific case, they approximate the Tukey depth and the Tukey median. And they are polynomial algorithm, and actually, this is a new result. So all the previous results on approximating the Tukey depth and Tukey median are exponential in terms of the dimension, and this is a polynomial in the dimension. But I must say that usually the approximation that they consider is different than the type of approximation that I'm considering here. But nevertheless, this is something that is it's a new result. We can also, I'm not going to go over the details here, but we can also discuss the geometrical properties of this depth function, and if it is convex in some sense, but I'm going to skip that. But this is the big but, right? So as you noted, I didn't have any empirical study over here, which is kind of, why don't you have any, if it's good, show us that it's good. And the problem is that I made the assumption that I can sample functions from my belief. So all the algorithm used actually, if we look at the algorithm that approximate the median, we needed three things as inputs. We needed a sample of unlabeled instances, which is usually easy to get. We needed a consistent algorithm, which in many cases is easy to come up with. But what is hard to come up with is just sample of functions from my belief. This is something that for interesting belief distributions is not so easy to achieve. And so we can do heuristics, right? So you can think about Bagging and random forest and everything like that. This is actually what they do. So we can do heuristics. We can also show that if I can sample from the true distribution, but I can sample with something which is close to the distribution, that's fine. We can correct for these mistakes. But the reason why I didn't yet do the empirical studies is once you start using heuristics, and if it works, great. If it doesn't work, then is it because all this method is broken, or is it because the heuristic did not deliver what you expected it to deliver? You won't be able to say. So this is why I preferred first to complete the theory and know exactly what I want to achieve, and then separately try different heuristics and see how they perform with respect to this method.
Is there any way to measure how good maybe 2 is getting towards that, but is there any way to measure how good a heuristic is with respect to a fair sample on Q?
Sure, its Bayes error is low. I mean, you don't know if it's the lowest one, but you can compare heuristics by comparing it.
You can compare heuristics, yeah, but can you tell if you're...
But you can compare it. You want to compare it, again, you want to compare this Bayes error. So if its Bayes error is low, then you're good. But if it's not low, is it because the heuristic is broken or because your posterior is not very decisive or not very good? It's hard to isolate these two things, and this is why I want to isolate the theory from the empirical, because there is this additional unknown over here.
I'm a little puzzled by the hard Q comment. So it seems like in a lot of cases you can use Markov chain Monte Carlo to sample from the Q.
To approximate. So even if...
Well, you can draw, now the question is whether or not it's converged or not, but I think...
So for example, even if you have, in the simple case, where you have uniform distribution over a convex file, right? So yeah, there are a polynomial algorithm for sampling from that, and they are polynomial and they have improved. So the complexity is something. So the first algorithm were something like with a complexity d to the power 23, and they managed to reduce it all the way. Now it's something like 3 or 4. But the constant here is something like 2 to the power of 100.
But even like there's been literature on like finding mean instead of the posterior, and there are a lot of approximation algorithms like EP or Laplace approximation that would actually give you a very good distribution of Q with respect to the kind of family that you
So again, there are a lot of heuristics on how to do that, and there are evidence that in many cases they work fine, but the only result that I know that is actually samples from the distribution, at least in some cases, they have this complexity. So again, if once you start...
There are certainly other cases where you know that the Markov chain is mixing and you're going to get samples from the distribution.
You're making a very strong assumption that you have to sample from a polytope and you're only sampling, continuous values from a polytope. But that's one specific.
True. But then if you say, okay, so let's sample only from Qs from which I want to sample. So maybe these Qs. So if imagine now I'm going to apply it to a certain problem. So first of all, let me just, before we dive into this discussion, the first thing that I want to do is really go ahead and evaluate that, right? So this is, obvious, right? But there is a reason why I wanted to isolate it from this theoretical work. And because once I want to do that, I have to either restrict the type of Qs, the posterior that I'm allowed to use, to only Qs from which I know how to sample from. Or say I'm not going to restrict Qs, but I'm going to use some heuristic to sample from this distribution. Anyway, if it works fine, that's great. But if it doesn't work, what does it mean? Does it mean that this full method is broken, or does it mean that if I restricted my family of distribution, I restricted it in a way such that this distribution do not work well for this problem?
But by definition, since your method has to sample from Q, it's broken if it doesn't work.
Yeah, but then you can say okay, it's okay, so I can say there is another item now is how to sample from Q, right? So I went that far, and obviously there is still a way to go, right? And I'm very clear about it. But if I just evaluate now and see if it's working, we are happy, right? But if it doesn't work, what does it mean? That this whole line is broken, or that we need to improve our methods from sampling from Q?
Probably the latter.
Do you have any concrete ideas of what types of cues you're interested in sampling from?
So, for example, log concave.
Yeah, so exactly the kind of the energy function you have.
Yeah.
They have a ton of work in trying to approximate the posterior for those guys, like at least in the Bayesian inference community.
Yeah, but
specifically even with like SVM loss functions, with logistic loss, with probit loss. And
as far as I know, and I'll be happy to know that I'm wrong, as far as I know, none of them has provable guarantees on the difference between the true distribution from which you sample and the distribution that you're trying to sample for. You don't have, so, all of them are well justified, seems to be working, but for none of them, apart from this result of Lovas and Simonovitz and stuff like that, and I don't remember who else,
here's the problem.
none of them is really provable.
No, so here's the problem, right? So you talk about sample selection from this posterior distribution, and you're saying that your method of selecting a median is a good one, right? And then I have methods to evaluate the mode. I have the methods to evaluate the mean, and in certain cases people have shown that the mean might be better than mode, right? And I cannot pinpoint where does this median lie in that space, unless there is some empirical evaluation,
Sure.
right? And hence my questions, right? What would it require for you to sort of show that it is as competitive as those guys?
So definitely I'm gonna evaluate that, and definitely I'm gonna try these heuristic methods, either of sampling with the inaccuracy of the sampling process and see if it works, or otherwise restrict the family of cues such that to families from which I know how to sample. But I wanted to separate that from this work because, I'm once I do that, I add another unknown, and the evaluation would be problematic.
But it's always tangled. Here's another way of looking at it. It may be the sampling when I sample a posterior. I see that really is my posterior because I can adjust my prior. It's whatever I say. So I can adjust my prior, maybe if there's certain conjugacy things, I don't know, to say that is my prior. It's a crazy prior. But how can you argue with me? It's my prior, and the prior happens to match where the posterior has the sample.
That's true. But again, think about, you are now to design an experiment, right? You are now to design an experiment. And you think, okay, I'm going to design an experiment. Let's see what are the possible outcomes, right? If the outcome is that it does not generalize well, is it because of your sampling technique, or is it because the algorithm that I described here?
Maybe this will take us offline. I think they're just inseparable. I think it doesn't make any sense to even say that.
It would have been inseparable. It would have been inseparable if I simply knew how to sample from Q from a general Q. So, for example, from the energy function of SVM, if I could sample from this energy function, right? And then I can compare the result of the result of SVM. Then I know exactly, this is.
That's one choice of prior.
Yeah, this is one choice of prior, but important one.
Yeah, I can have my choice of prior, which corresponds.
It's true, but then again, what is the broken component here? Is it the prior is broken, or is it the algorithm broken? So there is a problem in running these kind of experiments, right? It's an inherent problem in this kind of experiment, that you cannot control for all the free variables.
That's true.
Right? So this is why I prefer to go all the way to establish a theory and know exactly what I want to achieve, analyze it, and then once I do that, I'm going to run the experiments. But I know that there are my ability to evaluate the result of this experiment is going to be limited.
So if I understand correctly, you're saying that the depth of the Bayes classifier is half, and then your bounds have 1 over the depth. So you're going to pay a factor of 2 in your error compared to the Gibbs sampler, no matter what. So I mean, the whole.
If you remember when Mario Machan was over here, he said we get this annoying 2-factor for analyzing the Bayes classifier. We tried to get rid of it and didn't manage to do that.
No, he has a paper where the 2 goes to 1 plus epsilon in some settings. But
I don't know. At least here, when we're studying on this stage, he said that we have this annoying 2-factor. And we tried to get rid of it, and we couldn't. And
he has a paper.
You can see cases in which you can get better than 2. For example, if this the relaxed depth. So we can say, why is it 2? It's 2 if you have many points on which kind of the majority vote is very marginal, right? But if you actually, for most of the point, the majority is very decisive, actually this bound will show you that you can get better than factor 2. Kind of 2 is the worst case for the Bayes classifier. It could be better. But even in their analysis, actually what they show, the best bound that they get is for the expected Gibbs classifier. Yeah. And then they say, okay, the Bayes classifier cannot be much worse than that. And this is the same thing that we do over here.
So remind me, I'll show you this result where the 2 goes to nothing. The other thing I want to say is that the trendy thing in learning theory now, right, is to talk about the importance of strong and convex regularizers. And you didn't mention this at all. All you really required was the log concavity of the posterior. Now what happens, I don't know what it would be called, when you have a posterior which is defined as normalized x of a strongly convex function rather than just a convex function, which would be achieved by a strongly convex regularizer. And I think what you would get is that you had this guarantee that said that there exists a function which is at least, of depth at least 1 over e.
1 over e, I don't need the strong convexity for
right,
that.
but I'm saying I think that if you, okay, so 1 over e is in the general case. If you have a ball, you actually have half. Mm-hmm. I think strong convexity will exactly interpolate between the 2, right? This would be analogous to this, so you taught me this result, that for a general convex body, the center of mass, you could cut it such that at least 1 over e is on one side. Yep. So I'm assuming that's like this 1 over e. Yep. But if you have a ball, you can actually cut it in half. Mm-hmm. And then if you have a strong convex regularizer, like an L2 regularizer, think of your loss function as just an L2 regularizer, no empirical loss. So the weight of the empirical loss is 0, and you're just doing quadratic. Then you have a ball. Then you have half.
Interesting direction. It's not something that I can come up with from the top of my head. Actually, you can also show that if the function is not log concave, actually there's a larger family of distribution which is called raw concave function, and for each one of them you can get a bound which is a function of raw, and you can refine these results, I'm sure.
There's a question about the energy function that you're showing, right? The regularizer plus the loss function. Does it always lead to valid probability distributions? I'm just wondering. So if you just exponentiate the energy negative.
Oh no, you always have.
I think for SVM probably it does not.
So you always have the partition function.
Yeah, but I think for some cases you cannot sum it up to one. So consider the case when you have, like SVM case, when your regularizer is a L2 norm, whereas your loss function is a hinge loss.
So you say that the integral might go to infinity, and you cannot.
Yeah.
Could be, but then if you bound it in so bound everything.
So you have to approximate it somehow.
Thank you very much.